Welcome to our discussion about current and resistance. So this is chapter 22 from the textbook College Physics. Let's get it going. All right, so we're going to start with the idea of current. And current is when a charge moves from positive to negative. Often we think of that charge moving along a wire. That's where most current would move if we are like creating a circuit, for example. And charge always moves from positive to negative. And when that happens, the wire can get hot. Or if there's some kind of resistor in there, like a light bulb, that bulb can glow. So here I have an example. The current would start at the positive side. It would run through the wire in that direction towards the negative side because there's a charge differential, right? There's a whole lot of positive here and a whole lot of negative over here. And as the charge moves from positive to negative, that means it's going to go through the wire, and that's going to increase the temperature of the wire. That's called short circuiting something. There's no resistance in there, so it's just going real fast, and that creates a lot of heat. Or if you have a resistor, like a light bulb, then the filament can create a lot of resistance, and that leads to it getting hot and glowing. So basically, we're just concentrating where the heat is there, and that causes the light bulb to glow and put out some light. Cool, same deal. Charge goes from positive through, and then through here, over here, down here, and then continues over to negative. So it's just a different part of a wire. Okay, so what does it actually look like when current is happening? So if each of these red dots is representing an atom, and then the blue arrows here are representing an electron, we have an electrical field that's going in this direction over here. And so these atoms are sitting in this electrical field, and the electron is going to kind of do some jumping. It's going to jump between atoms. Now, we think of current as like the electron just zipping in that way, but that's not actually what's happening. So that's not really accurate. Instead, it's doing a lot of jumping from atom to atom, and it's not always a smooth, straight pathway, which means the electron itself doesn't make a ton of like distance progress. When I turn on the light switch, the lights go on immediately, but it's not the electrons from the light switch that are going all the way up to the light. It's almost like they're holding little balls and they're just like passing the ball to the next person, and they're in a whole matrix, so they're passing them in lots of directions. And overall, a ball is getting pushed into the light, but it's not the first ball that was passed. So the electrons are being kind of like pushed, jumped from atom to atom, and the atoms are sharing the electrons as they move, boop, 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 etc. Generally making progress against the direction of the electrical field. So the electron is going opposite the charge, right? The charge is positive, and so it's moving in the electrical field direction. The electron is actually negative, so it's moving the opposite way. So that electron is jumping erratically, and it's jumping opposite the field. If we look at that on like an extended wire, this is not a handle, it's supposed to be a wire between a high potential source and a low potential source. So high potential would be lots of positive charge. Low potential would be lots of negative charge. The charge is the red arrows, and it's going from positive down to negative. The electrons are going the opposite direction. They're going from negative to positive. So the things that are actually doing the moving are the electrons, right? The electrons are doing the moving from negative to positive, but we still say that the charge is moving from positive to negative because when we came up with the concept of electricity, we as humans, we didn't know that electrons existed. And so we just had to set that the charge was going one way, and we set positive to negative down the gradient, which makes sense, right? From higher potential to lower potential, it's just that by chance electrons are negatively charged, so they move the opposite way. And we didn't adjust our naming convention to solve that. All right, so current goes from high potential to low potential. It goes down the gradient, and the current goes opposite the electrons. All right, and then finally, if we look at the current, at A versus B. So I have one point right here, point A, and then I have another point right here, point B. How would the current compare? Well, there's only one pathway. The pathway just goes straight through here, then up and around through there, and then straight through there. And so since there's only one pathway to go, the current has to be the same all along that pathway. So the current should be equal, right? A equals B. So the current at A equals the current at B. I is the abbreviation for current, the variable. All right. So let's just kind of define what current is. Current is the change of charge in a given time. And we use the unit amperes, which is abbreviated A, and an ampere is equal to a coulomb per second. A coulomb would be the unit of charge, second is the unit of time, so coulombs per second give me an ampere. We use I for the variable for current. I don't know. So that kind of defines current for us. All right, what we know about current is something called Kirchhoff's junction law. And basically it says whatever current comes into a junction has to be the same as the current that goes out of a junction. So if you think about this as cars into an intersection, however many cars come into the intersection, we have to have the same number of cars leaving the intersection. Or water through pipes. Whatever water comes into the pipe split has to be the same amount of water that goes out of the pipe split. It doesn't have to split totally evenly. So if I had, say, 3 units coming in here, let's say 3 amps, I could have 2 amps coming out here and 1 amp coming out here. But they do have to add up to the total. So 3 equals 2 plus 1. Same deal if it's multiple things coming in and 1 going out. So I could have 4 amps coming in here, 6 amps coming in here, and that means I'd have to have 10 amps leaving out there. Whatever comes in has to be whatever goes out. So the total sum of the currents in equals the total sum of the currents out. So let's do a little sample. I've got a junction of 5 wires, and I know 4 of them. And then I'm trying to figure out what would be coming in or out of this last one down here. All right, so in total, coming in, I have 3 and 4. Okay, so coming in, I've got 3 plus 4. And then going out, I have 2 and 6. So 2 plus 6 out. That means in total, I've got 7 in and 8 out. So in order to balance them, I would need 1 more coming in. So this one has to be going in. All right, I'll use a different color. So this must be an in current, and it must be 1 amp, because 7 plus 1 would equal 8. And then I'd have 3 plus 1 plus 4 equals 2 plus 6, and that would match. Cool. All right. So let's do a little stop and think. The discharge of a capacitor lights 3 bulbs. Comparing the current in bulbs 1 and 2, we can say that the current in bulb 1 is greater than the current in bulb. Okay, so we have current coming through here, and then the current has to split in 2 ways, right? It goes through 2 and 3, and then it comes back together here and goes through bulb 1. So bulb 1 gets all of the current. Bulbs 2 and 3 only get a part of the current. And we can estimate it as it's probably about half if the 2 bulbs are the same. So bulb 2 is going to get less current, and bulb 1 is going to get more current. Bulb 1 gets all of the current, bulb 2 only gets a fraction of it. Okay, so current in bulb 1 is greater than the current in bulb 2. Yes, that is true. Current in bulb 1 is less. No. Current in bulb, no. Okay, so the current has to split, and then all of it goes through 1, so A1 has more. All right, let's talk about one of the sources or the pumps for current, which is a battery. So one way of thinking about a battery is to think about it as a charge escalator, which basically means it increases the potential energy of the charge. So we've here got like some little charges, our little plus signs, and they're on this like little charge escalator. Now, just to be clear, inside of a battery, there's not actually a little tiny escalator. That would be very, very cute. This is more of like a model or a way of thinking about what's happening in a battery. So we've got a negative terminal in the battery and we've got a positive terminal in the battery. And inside that battery, there's some ion flow, which leads to the charge increasing in potential energy. So from the negative to the positive, I have an increase of potential energy, and I call that increase of potential energy the voltage, or the change of V for the battery. Then, as it goes through the wire here, as the current runs through the wire, it decreases its potential energy by the same amount that it was increased in the battery. So if this is, say, a 1.5 volt battery, the battery would be plus 1.5 volts. And then as it goes through this wire, it would have a total decrease of minus 1.5 volts. So it's back down to 0. And then it gets increased again. And it's basically like go up, go back down 1.5, go up 1.5, go back down 1.5 in terms of potential energy. And that's a rough approximation. It's a good model or metaphor because we've been thinking about potential energy due to height. And now we're thinking about electrical potential energy, which is not due to height. It's due to charge and voltage, but voltage is kind of approximate to the potential energy difference. It is a potential difference. So the charge escalator lifts the charge from negative to positive, charge gains energy, and then it loses the energy through the battery. And that loss of energy through the wire is why the wire would get hot. All right, so we call that voltage, but you can also call it EMF if it's through a battery. And for EMF, they use the script E. We're going to see voltage or V a heck of a lot more often. So I'm going to say that really the variable is going to be V, although your textbook will sometimes use the script E for EMF. And the unit there is volts. And that is the potential difference. So let's think about that. A battery produces a current in a wire. As the current continues, which of the following quantities, perhaps more than one, decreases? Okay, so it increases as the battery produces current. Okay, as the current continues, what happens in the battery? Got it, which decreases? So the positive charge in the battery. No, because every time, like in one sense, you'd think, okay, yeah, it's putting a positive charge out here, right? And so that charge is going away. But at the same time, there's a positive charge that comes back in. Remember, the positive charge isn't going away. It's just being transferred through the wire. And it's almost like every single molecule is holding an electron, and then they just pass the electron and take the electron from the next one. And then they pass the electron and take the electron from the next one. So the charge doesn't go away. It just gets transferred out of the positive and then back into the negative. Or the electron gets transferred out of the negative and into the positive, which way you want to think about it. The EMF of the battery. So that's like the voltage. And if this is a 1.5 volt battery, it stays a 1.5 volt battery. So voltage is constant. The chemical energy in the battery, yes, that one does decrease. If I use a battery, it loses its energy, and then we would say it's like a dead battery. It doesn't work anymore, and your smoke detector starts beeping. So that does decrease. All right. Electrical field and current inside the wire. So this is just another representation showing our little charge escalator here, showing a potential difference, the change of voltage of the battery, and how that charge gets pushed through the wire, creating a current. So in 2216, the wire is changed to a new one, leading to increased current in the wire. Compared to the original wire, the potential difference across the ends of the new wire it would be the same. So it's the same battery, right? And the battery is the thing that is creating the potential difference. It's as if it's a 1.5 volt battery, it's still a 1.5 volt battery, and AA batteries are 1.5 volt batteries, which is why I keep using 1.5 volts. So whatever the battery is, that's what's creating the potential difference. That's what's creating the voltage. So even if I change the wire, I might increase the current. I could change the resistance, but the voltage stays the same. And the voltage is the potential difference. All right. Wonderful. So let's talk about resistance. So resistance we can represent using the variable R. The unit for resistance is ohms, which is an upside down horseshoe. It's the Greek letter omega, capital omega. We've used lowercase omega for rotational velocity, the funny looking W. So funny looking W is the lowercase, upside down horseshoe is the uppercase. But up for capital omega, it means the unit ohms, which is a unit of resistance. And resistance is equal to the change of voltage over the current, or R equals V over I. And then for units, that means that an ohm is going to be equal to a volt divided by an amp. Okay, so it's volts divided by amperes. And then if we look at like how we can change the resistance, so there's a few factors that would change current in a wire. The first one is not changing the resistance. The first one is just I add more voltage. If I increase the number of batteries, if this is say a 1.5 volt battery, then this would be 1.5 volts plus 1.5 volts for a total of 3 volts. So by increasing the voltage, that will lead to twice as much current, assuming the same resistance. All right, so this will double up your current is by increasing the batteries, increasing the voltage. Another thing I could do to change the current would be to change the resistance of the wire. So a short, thick wire has very low resistance, which means the current is going to go real fast. Big current through an easy to go through wire. A long, thin wire is going to be harder to get through. Think of these as like pipes. If you have a really itty bitty tiny pipe, the water doesn't have much space to get through. And so it's going to go a lot slower. And so the current is going to be a lot slower. So we're going to get less current in a more resistant pipe, more resistant wire, by making it longer and thinner. And then the other thing I could do is I could change the wire material. So the material itself influences the resistance. So copper has very low resistance, so it carries a larger current. Iron has a little bit higher resistance, so it's going to have a smaller current, which is why most of the wires inside your house are copper wires. So like most of your electrical wires would be copper because they have very low resistance. And that allows you to use slightly smaller gauge wires to carry the same electrical load, the same electrical current. All right, so let's look at the resistance of a light bulb. The glowing element in an incandescent bulb is the filament, a long, thin piece of tungsten wire that's heated up by the electrical current through it. When connected to 120 volts of an electrical outlet, a 60-watt bulb carries a current of 0.5 amps. What is the resistance of the filament in the lamp? Okay, so I need resistance, and I know that resistance equals the change of voltage over the current, and I have a voltage, there's 120 volts of electrical outlet, and I have a current, 0.5 amps. It gives me 60 watts, but that's not actually necessary. We haven't talked about power yet. So that would be 120 volts divided by 0.5 amps gives me 240 ohms of resistance. That ohms looks a little bit funky. There you go. So 240 ohms of resistance through the filament in the light bulb wire. All right. So we can also find the resistance of a specific wire or a specific material based off of its resistivity. Resistivity. So the equation for that is that the resistance is going to be equal to the resistivity times the length of the wire divided by the cross-sectional area of the wire. So that's like the size of the circle of the wire. So that would be resistivity. And for resistivity, we happen to know the resistivity of a whole bunch of different materials. We generally start with metals because those have very low resistance. They're excellent conductors. So the lower the resistivity, the less resistance, the less it stops the flow, the greater of a conductor it is. The more it stops the flow, the higher resistance it'll have. So these are really big numbers, like pure water and a cell membrane have super high numbers. They are really good insulators. So fat is a pretty good insulator. Some electricity could get through, but not a whole lot. Copper is a great conductor. You can see it has a very, very low number, 1.7 times 10 to the negative 8th. So that's going to make a big difference. And then some, you'll notice that it changes depending on the temperature. So tungsten is less resistance if it's cooler, that's at room temperature. If you make tungsten really, really hot, it provides a little bit more resistance. Interesting. All right. So let's go with that. The length of a light bulb filament. Okay, so same deal as previously. We're still looking at that light bulb filament. We calculated in 22.5 that a 60-watt light bulb has a resistance of 240 ohms. I remember that. At the operating temperature of the tungsten filament, the resistivity is approximately 5 times 10 to the negative 7th. Okay, so that means the tungsten must get really hot, like 1500 degrees Celsius, when it's inside that light bulb. If the wire used to make the filament is 0.04 millimeters in diameter, it's very, very thin, how long must the filament be? Okay, so I have the resistance. I'm going to use the equation. Resistance equals, it's not a P, it's like a, there you go, times L over the cross-sectional area. And then how long must the filament be? So I need to solve for L, which means L equals multiply A over, it'll be RA over P. Not actually P, but okay. So now the area is the other one. The area equals pi r squared, which equals pi times the radius. Now that's the diameter. So the radius would be 0. Now this is 0.04 millimeters. So I got to put 3 extra zeros in there because there's 1,000 millimeters in a meter. So 0.000, okay, 0.4, nope, 0.2 because I need the radius. So 0.2 meters squared. That means the area equals, that's probably going to need a scientific notation. So that's 1, 2, 3, 4, 5, 10 to the negative 5. 2 times 10 to the negative 5 squared is going to give me 4 pi times 10 to the negative 10 meters squared. All right, so now I can plug that in for the area. The length is going to be the R resistance was 240 ohms times the area, which is 4 pi times 10 to the negative 10th meters squared, all of it over the resistivity, which was 5 times 10 to the negative 7th ohms meters. Okay, so units wise, ohms will cancel. One of the meters will cancel, leaving me with meters. So far I'm in good shape for a length. Then math-wise, numbers-wise, -7 on the bottom, 10 to the negative 10 on the top will cancel. Let's see. Let's do this right. Cancel that, change that to a -3. 10 to the negative 3 now. Okay, so 240 times 4 pi divided by 5 is 603. And then 603 times 10 to the negative 3 is 0.60 meters, which is about 60 centimeters. So that's pretty nice. That seems like a reasonable length, right? Obviously 60 centimeters is pretty long, but you'd have to coil it really, really, really tight. And if you look at it, the wire inside of a light bulb is coiled really, really tight. Nice. All right. So let's do a little stop and think. A wire connected between the terminals of a battery carries a current. The wire is removed and stretched, decreasing its cross-sectional area and increasing its length. When the wire is reconnected to the battery, the new current is, okay, so I'm just having a tough time reading. A wire is connected between a battery, good. The wire is removed and stretched, decreasing the area, increasing the length. The new current. Okay, so first I'm gonna have to figure out the new resistance, and then I'm gonna use the new resistance to figure out the current. So if I decrease its cross-sectional area, so the equation I would use would be R, it's not gonna show up, R equals L over A. So that is a constant. It's the same wire, so that's a constant. Don't worry about that. The length increases. The area decreases. So that means the resistance is going to increase quite a bit, right? Because it's directly proportional to length, inversely proportional to area. Those are both going in the same direction. So the resistance would increase. Since the resistance increases, the next part is checking resistance equals voltage over current. So those are inversely proportional, right? Resistance equals voltage over current. The voltage hasn't changed. It's the same battery. Resistance went up, which means since they're inversely proportional, the current has to go down, because 1 over a smaller number is a bigger number. Okay. So the current goes down. The current is less than the original current, which makes sense. More resistance, less current. All right. So far, so good. We're going to pause there and then come back for part 2.